This section is about parametric equations. It's one of my favorite areas in math because it allows you to make all sorts of animations. Pretty much every animation you see me making Desmos, I'm using parametric equations to make it happen. So I'm going to kind of get your feet wet with this little warm-up problem. What I recommend right now is just pause this, fill in this chart. You've been given x equals 2t, y equals 3t, and I've given you some t values, so plug those in and see what you get for x, see what you get for y. And then again, take a moment, fill this out. When we come back, I'll have it filled out for you. So there's the chart filled out. That's what you should have when you get done with this. The next stage is to put this on a graph. So I had 2, 3. I had 4, 6. I had 6, 9. And then a lot of the points got off the graph here. So what's happening is it's making a line. And some important things here. It started at 2, 3. That was the first point I was given. And it moved in that direction. So when you do parametrics, they're actually working something out that's moving in the real world. What's happening in the background here is, even though I'm doing a two-dimensional graph with just x and y showing up, there's t working in the background, which is time. So this graph allows me to show motion through time in a two-dimensional space. So basically, I'm fitting an extra dimension in here. It's one of the kind of neat things about it. In a two-dimensional space with just x and y, also allowed to sneak in a third variable. So it kind of gives us a little more flexibility than a normal equation does. So to officially start the notes, I'm going to start you off with a little question here. And when you come in class, I'll have a little demonstration of this with a penny, dropping it and throwing it at the same time. So the question is, what hits the ground first? A bullet fired from a gun straight out, or a bullet dropped from the same height as the barrel? All right, so it's important that it's fired straight out, horizontal, because if we aim up or down at any amount, it's going to go down faster. If we shoot it up in the air, it's going to be in the air for a long time. So straight out, horizontal. And if I dropped a bullet at the exact same time, just literally dropped it as soon as I fired it. So which one is going to hit the ground first? Right. So let's kind of run through what it was going to look like. This is the bullet that I just literally dropped. So as always, all these Desmos demonstrations are posted on the website. If you want to open them and play with them yourself, you're welcome to. So as time moves on, it drops. Okay. Probably not surprising at all. And also, you should probably notice it's accelerating as it falls. It's falling faster as time goes on. Okay, that's important. Let's add in here now the bullet that I'm firing out of the gun. So now they're going to both, one's going to go out, one's going to go straight down. And let's see if we can answer the question, which one hits the ground first? Well, it looks like they might hit at the same time. Let me scoot that over so we can see where that actually hits the ground. It's looking like it's the same time. So to add in another line here we can put to see if they're actually falling at the same time, falling the same rate. And it looks like they are. It looks like they're going to hit the ground at the exact same time. And that's what should be happening. At this time, let's try the path of a baseball that's been hit. So the parabola is just there to show the path it's going to take. So there it goes. It's following the parabola. Probably not surprising when you hit a baseball, throw a ball. It's going to follow sort of a parabolic shape. So to help you understand parametric equations, what we're looking at is, how is this thing moving in the horizontal direction? How is it moving in the vertical direction? Okay. So before we get too deep into that, let's go back to the bullet for a second. The first one that I dropped, it's not moving forward at all. So the only thing we got to look at is what's affecting it up and down. Okay. And if I'm dropping something, there's really only one thing affecting it. And we probably all know what that is. It's gravity. It's pulling it down. It's accelerating it. So that's it. There's no effect forward horizontally. It's all vertical effect, and it's all coming from gravity. Now the one that I'm shooting out of the gun, it's equally affected by gravity, which is why it's falling at the same rate. But it's got forward velocity on it as well. Now in real life, it's going to slow down as it travels. And this gets into one of my favorite things in math, differential equations. You can literally explain the whole universe and boil it down into a few differential equations. It's really powerful stuff. So if you keep going in math, you'll eventually learn differential equations. They're pretty awesome what they can accomplish. Back to the baseball now. What I'm going to do is add shadows. to just think about the horizontal motion, vertical motion. So let's just figure it's a bright sunny day, it's noon, sun straight overhead. So we're gonna have a shadow underneath the ball. Let's just kind of watch its motion. So ball's traveling, shadow's moving across the ground. It's a nice, smooth, uniform, fluid motion. It's kind of going at a constant. All right. Now again, in the real world, air is going to slow the ball down. That's going to probably slow down a little bit, but again, that gets into the differential equations. We're not there yet. So pretend there's no air. It's on the moon. Here you go. You're playing baseball on the moon. Nice, fluid, smooth motion. The only thing really affecting the ball in this direction is how fast it came off the bat in that direction, forward in that direction. Okay. So now let's add in the vertical shadow. Ball goes up, kind of peaks out, and accelerates downward. Watch that acceleration, okay? Goes up pretty fast, slows down, slows down, slows down, peaks out, slows down, follows slowly, and then speeds up. All right, so probably none of that's very surprising. So let's think about what's affecting it. We know gravity's pulling down on it, for sure. And gravity's pulling down constantly. That's why it slows down, peaks out, and then starts moving downward again. The other thing that affects it is how fast it comes off the bat vertically. Okay, how much speed does it have upward when it comes off that bat? So there's really two things here. And I guess the third thing, and I didn't really count for this, is how high off the ground is it when it gets hit? It probably makes sense if I hit a baseball off the top of a building, it would go a lot higher than if I hit it off the ground. So that's the three things that are really impacting this. How high is it initially? How fast does it come off the bat? And then ultimately gravity, how much does it pull down? Let's formalize what we just said, put it in writing now. So think of the motion as an X position and a Y position at any given time. So what's affecting each position? So let's watch the baseball one more time. This time we've got both shadows on and the ball itself. So let's put it in motion. And horizontally, just forward velocity. But in this direction, we have gravity pulling on it, and definitely how fast the ball was hitting the air, possibly how high off the ground it started as well. So we'll put all that stuff in here. So again, for the X direction, just forward velocity, that's it. Now I'm using that word velocity. You're going to see a lot of things from back in chapter 6 with vectors come up today. This is going to tie into physics, so you're going to see a lot of that stuff back again. All right, for Y, gravity is probably the number one thing. And here's the other thing, it's negative. Gravity, as far as plus and minus, just think about coordinate plane. Which direction is it going? Forward velocity, that's to the right, so positive numbers. Gravity's pulling down, so that's toward the negative numbers on the Y. I'm hitting the ball up, so that's toward the positive numbers. So negative gravity plus, we'll say upward velocity. And then also, if there's any initial height, that matters as well. Now there's something else we've got to consider with these. I asked about position. That's an XY coordinate at any given time. Position, how far away? If I start right here, how far from that am I? In the X and Y direction. So these are both positions. Okay, distance. Think of it X and Y distance. So to get everything to match up, forward velocity is not a distance. Driving down the interstate at 70 miles an hour is not a distance. If I'm going to figure out how far I traveled, what else do I have to do? Well, I went 70 miles an hour for 10 minutes. Once we've got a time in there, now we can figure out exactly how far we should travel. You take your speed times your time, and the reason that's going to be true, speed is something like miles per hour, and if you multiply that by the number of hours you traveled, you end up with just miles. So we do need to say times time for velocity. Same thing down here, upward velocity times how long it traveled at that speed. Height is already in terms of just feet. If you want to do feet here, meters, whatever you want to go with. So that's good. Velocity times time gives you a distance as well. So that's a distance, that's a distance. Acceleration. Acceleration is kind of weird. So you're falling, whether you do meters per second or feet per second, whichever one I'm used to feet per second, so I usually go with that one. But every second you fall faster, right? So your speed in feet per second, maybe I should start there. Your speed per time. How much does your speed change from 1 second to the next? So if you took this speed and then your speed 2 seconds from now and divided that by 2 seconds, that tells your acceleration. What was your change in speed over time? So it's kind of weird. It's feet per second, because speed's feet per second, time, in this case, would be in seconds. So you do, however you want to work that out, flip and multiply or whatever, that's feet per second squared. So kind of weird idea at first, but you'll eventually get used to it in physics. What that means is for your time over here is we need to actually square the multiply times time squared. Because that would be time times a second, seconds squared, kind of cancel out, that's the logic behind that. So that's the way it's got to go. Velocity multiplies by time, gravity times time squared, or acceleration ultimately. Velocity times time, height's already a distance, so that's good to go. All right, you did something similar to this already in chapter 6 with vectors, so this is kind of picking up where you left off. You did the velocities for this already, so this should look familiar. Now we're going to take it a little bit further and make parametric equations out of it so we can model this. We'll put it in a calculator to see what happens. So model the path of a baseball hit 3 feet above the ground, 30-degree angle, at 100 feet per second squared. Or sorry, just 100 feet per second. And gravity is negative 16 t squared, just to make it simple. So the baseball is traveling at 100 feet per second, but it's traveling at a 30-degree angle. And this should look familiar from chapter 6 with vectors. It has some forward velocity, it has some upward velocity. We can analyze those vectors. Now let's set these up as trig ratios. So I'm going to start with cosine of 30 with Vx over 100. I'm not going to worry about units right now. I just want to get the numbers at this point. Sine of 30 would be the opposite over 100, so Vy over 100. Now let's go ahead and solve these things. Vx would be 100 times cosine 30. Vy would be 100 times sine 30. And since these are things that would be on the unit circle, let's go ahead and reduce them some more. So Vx could be further reduced to 100 times. Now cosine 30 is square root of 3 over 2. So 50 square root of 3. And I'll go ahead and put feet per second there. It's probably good to put the units on it. Vy, well, sine of 30 is a half. So half of 100 is 50. And again, I'll put the units on there. So 50 feet per second. So there's my forward velocity. There's my upward velocity. To make parametric equations, now let's just look at what's affecting the position. These are positions again. So in the forward direction, the only thing really affecting position is how fast it's traveling and how long it's been traveling. So I'm going to take my horizontal velocity, 50 square root of 3, and I'd like to make sure I multiply that by time. And that's it. That's my position at any given time is based on how fast it's moving. Y has a lot more going on. You've got, first of all, gravity pulling down. Now, I gave you negative 16t squared. I'm trying to let you kind of get your feet wet with the physics if you're not used to it, because most people take this class take physics next year with calculus. So these are things you're going to see again. But for now, just know gravity is negative 16t squared. If you get that in there, and that explanation fully makes sense, but if you get that in there, it's going to work out. So gravity's pulling down. We're hitting the baseball upward, so it has an initial velocity upward at 50 feet per second. So plus 50. And that's times time, because I need my speed times how long it's been traveling to figure out my distance I've traveled. And finally, it does have a little bit of initial height. We hit the ball 3 feet off the ground, so plus 3. So those are your parametric equations. I do want to show you how to graph these. So let's pull up the calculator. And there's some old stuff I had. Let's clear that out. First up, we need to get this thing in parametric mode. So go to mode. And down here where you have function currently, you've probably been in function your whole life, come down there and go to parametric. One more thing to be careful on with these problems. I'm in degree mode because it was 30-degree angle. Now, I went ahead and did the trig ratio, so it shouldn't matter, but it's a safe practice to, if it gives you degrees, go ahead and put a degree mode. If it doesn't, but there's an angle and you know it's in radians, put it in radian mode. That way you're safe just in case. It's just a good practice to do. So make sure it's in parametric mode. And degree mode right here is a pretty good safe thing to do. Now to graph it, we go back to y equals. It's going to look a little different though. When you pull up y equals, you're going to have x1, y1, or x1t, y1t. There's several xt, yt pairs. You have to have both equations to get anything to show up, because each one is doing one's the x coordinate, one's the y coordinate. But you can put multiple equations in here if you'd like. Now I've already got them typed in. One thing to note, you're seeing t's. When I hit this variable button, it used to be x, now it's a t. And just to kind of point out, we're getting ready to do polar coordinates after this. So when you hit this button, you'll have a theta show up. And there's also a sequence mode that it comes up sometimes in the homework problems back in chapter 8. If you do sequence mode, you hit this button, it comes up as an n because it's the a sub n term. So anyway, that's what's going to be different when you hit that variable button. Another thing back here, I want to show you this. This is my preferred graphing type. It looks kind of like a little key. But here's some other options. Let's kind of run through the basics. You can do a line, you can do a dotted line, you can do a solid or extra thick line. Again, there's the one I like. What that does is it shows the ball and it shows the path behind it as it goes. If you want to, you can do just the ball or just the object in motion. So if you're trying to make an animation without any pathway behind it, that's kind of nice to see. I want to see both right now. I want to see an animation. We'll see this thing in motion, and I'm going to see the path that it took while it's graphing. So I'm going to go with that. Now I'm going to get a little over eager here and just dive right into hitting the graph button. And it's probably going to look kind of weird. All right, let's see. How do I tell it okay? There we go. Let's try hitting the graph and see what happens. All right, that's not exactly the path I expected a baseball to take. I was expecting a parabola shape. So we do need to make sure we understand how to adjust our window. And there's a few new pieces here, so make sure you understand what they are. Remember, parametrics, you still got your x and y coordinates as always, but you've got that third variable of time built in. So you have a minimum time of 0, that seems reasonable. Maximum time of 360. Now, I'm doing feet per second with all my calculations with my equations, so everything in time here is going to, by default, be in seconds. That's a long time for a baseball to be in the air. 6 minutes? Yeah, I don't think so. So most home runs are probably in the air like 7 seconds most. This is a little line drive hit. It's not going very fast. So I'm going to go with maybe 5 seconds. I believe that's going to be plenty to get the entire path of this hit. And just note that the way I'm going to do the window, it may not look like a line drive hit. I'm just saying in the real world it probably would. Time step, this is how much time is in between each point. Right now it's set at 7.5 seconds. So probably imagine a line drive baseball hit, it started here, and the next point you see is 7.5 seconds later, it'd be underground. And that's why I'm seeing that straight line look to it. So a safe time step is 0.1. That's a pretty good compromise. The trade-off here is if you make this smaller, you get more detail because it's graphing points closer together. But it takes longer to calculate. So 0.1 is a good compromise. You should get enough detail and it should move pretty quick. But if you want to see a little more detail, especially as we move on to some of the getting back into conics, and we're going to graph all those shapes again, some of those start to look like hexagons and things like that if you don't do the timing right. So sometimes you want more detail. Go a little smaller if you need to. Try maybe 0.05, something like that. You do like 0.01 or 0.001. This thing's going to stay here for a long time, several minutes, maybe even an hour or something. 0.1, again, good compromise. All right, X minimum, maximum, those are just like always. Now, again, let's make sure it says 0. X minimum, start at 0 feet. Now, I don't know, line drive hit 100 feet per second. I'll give it 300 feet, just that's giving it a lot. I don't think it's going to go that far. As far as the height, well, it needs to start 0 from the minimum. And it's sort of a guessing game. You can actually plug in numbers to your parametric equations, solve for time, and do all kinds of stuff like that. With some of the homework problems, you will need to do that. But as far as just getting the graph, let's just kind of play around here. Line drive hit 50 feet in the air, I think, is given plenty, so I'm going to put 50 up there. And I guess line drive is 30-degree angle, so it's not quite a line drive, but it's not a fly ball either. I think that's going to be pretty good. So let's go ahead and hit graph, see what we get. And yeah, that's a pretty good representation of it. And this kind of gave little snapshots. You probably noticed it looked like a ball actually traveling on that path, but it sketches the path as it goes. So just keep in mind, on some of these you're going to need to figure out how far the ball traveled or how high it went, things like that. So you can certainly use your calculator by hitting the trace button and just sort of going along the path here. Problem is, it may not, it's going to kind of go in the time increments you gave it. So we said 0.1 second, so that's how it's going to skip around. If you notice, it's counting about 0.1 second each time. So you might not land right on the point when it hits the ground, or right at the peak of the parabola. So just keep in mind, you may need to do some algebra here. You do know how to find vertexes by completing the square at this point. You do know how to find x and y intercepts. So if you want to find out when it hits the ground, well, your y would be 0 at that point. Find out how long it takes to hit the ground, and then plug it back up here to see how far it traveled at that time. You'll get used to some of those things. I don't want to give it all away because it makes you kind of think through the process, but just be ready to do some algebra like that on the homework problems. In this example, you're supposed to graph a circle with a radius of 5 and do it in parametric equations. Before I actually get into the parametrics, let's just go back to unit circle for a moment and kind of think about how this would play out. So if I pick any point on the circle, it has some x, y coordinate, and it's unit circle, so the radius is 1. So now let's kind of define x and y a little better, since that's really what's going to happen here with the parametrics. So thinking back to unit circle, thinking back to the one we just did with the baseball bat, cosine of the angle would be x over 1. So x would just be cosine of theta. Now you've seen that before, x is cosine theta. Similar logic, y is sine theta. And that's pretty much the beginnings of your parametrics, because parametrics just is the position as time changes, or in this case as an angle changes. With parametrics, time is usually the variable, but angles can be the variable as well if you're doing some kind of rotation, like a circle. So that's pretty much it. This x, y coordinates are your positions, and here's another way to define those. That's really where to begin. So x would be cosine theta, y would be sine theta. So this can be done in your calculator just as easy, but I like to do it in Desmos for the animation part of it. This is going to answer a couple questions we've had from earlier in the year. One being, why do you go counterclockwise when you go around the unit circle? And the other one that's similar logic is, why are the quadrants numbered the way they are? So I'm going to put this in motion, because that's what this lets me do. Now, parametrics and Desmos, if you want to do these, just go to a little plus, insert a table, and it gives you the XY option. Basically, each one of these is a point. So for the x1, which is the x equation, I put cosine of the angle. I use t for, you just got to pick a variable. You can do whatever. Use a for angle, t for time, whatever you want to do. Make sure you have a slider for that variable. I have t equals 0, so it's a slider. So yeah, cosine t for x, sine t for y, and I'm going to put it in motion. And there it goes. It's going in motion. This time or the angle moves forward, and it's going to etch out a circle that's going counterclockwise. Let me go ahead and put the actual circle itself up there. So there it is. It's going counterclockwise. That's why it goes that direction. And also, this is why your quadrants work the way they do. Quadrant 1, 2, 3, and 4. It comes from all this. So if you ever wondered about that, there answers that question as well. All right, so how do we make this thing have a different radius now? Well, if I wanted to go a little bit further out, then let's go back to how we generated this part. So I could put r here. If it wasn't a unit circle, if it was any circle, that would be r. So this would be r cosine theta, r sine theta. If you set up your trig ratios, that's how it would play out. So whatever the radius needs to be, I just need to put that number in front. So 5 cosine theta, 5 sine theta. And that's why right there. If you want a circle with a radius of 5, then cosine of the angle would equal x over 5. Solve for x, you get 5 cosine theta. Same deal for sine. Just use the y for the ratio there. So that's it. That's our parametrics. We'll flash back here, kind of show you how that plays out. So I made this where I can change the radius and You can see it happen there. So this is gonna be the one where I start off, let's see what I had a set for 1 at the beginning. Let's open that radius up to 5. So I'm plugging in 5 for my R value, so there's R cosine times R sine. A big part of this section is called eliminating the parameter. Basically, you're taking a function and turning it into a parametric set of equations, or you're taking a set of parametric equations and turning them back into a function. That's where the eliminating the parameter comes into play. So here's how it works out. Parametric equation introduces a third variable, typically time, sometimes angles, like in the case of what you just did with the circle. And if you eliminate that parameter, you go back to function mode. So that's just kind of an overview about parametrics and how they work. So here's an example. Write in rectangular form, which is just a fancy way to say function form. Parametric set is x equals 1/2 t and y equals t squared minus 4. So if they both hinge on this common variable t, we can use that with a little bit of substitution and work this out. Now, if it's going to be a function, ultimately it needs to end up being y equals. So the main logic you want to use is to solve for t here with x, and then plug that in. And at that point, you should only have x left, and it's already y equals, so that's kind of convenient. So let's try that. Let's solve this for t. We'll do that and multiply by 2 on both sides. That 1/2 times 2 would be 1. So 2x would equal t. Once I know that, then t squared would be 2x squared. And to wrap it up, 4x squared minus 4. I just want to show you a way you can check this whole eliminating the parameter idea in Desmos. I think this is the most efficient way to do it. You can do it in the calculator as well. The problem is the calculator does parametric mode, and then it does function mode separately. So it's hard to see the two things together. You can kind of see if the graphs look the same, but you can't see them at the same time. That's kind of frustrating. So in Desmos, if you do the parametric in a table, so here I have that x equation, 1/2 t, y equation, t squared minus 4. I just made a table, that's all I did. X equation goes in the x part, y equation goes in the y part. I did put a t in there, so make sure you put t as a variable. It usually will prompt you, it'll say, do you want to add slider t? And you just say, yeah. And then below that, I've got the function that I came up with, 4x squared minus 4. So all I got to do is just make sure the function is displayed, make sure the point's going to show up, and I'm just going to put it in motion and see if it goes through the motion like it should. So it seems to be following the parabola perfectly. And that brings me to a point that I skipped over up till now I need to tell you about. When we do this parabola, we need to make sure that we get the right direction. We need to actually put some arrows on this thing showing that it goes left to right. So here was our equation, 4x squared minus 4. All right, so that's going to have an intercept at -4. However you want to graph this is fine. If you need to do some of the stuff we did back in chapter 8 or chapter 2, I don't really care. Just get the parabola on the graph at this point. Y'all have done enough of this up till now, you should be able to do that. So I'm just going to plug some points in. If I put in 1 here for x, then 4 times 1 is 4, minus 4 is 0. -1 would be the same thing. This would be a case where it's an even function. That would make it really nice to find a point on the other side. So more stuff from back earlier in the year. If you plugged in 2 for x, all right, 2 squared is 4. 4 times 4 is 16. Minus 4 is 12. So we should be seeing 212. That's actually off the screen, so we'll just go ahead and put those points on there. That should be enough to get us going. So let's graph the parabola. Now, I put an arrow on that end, which is fine, but I really need to make sure my arrows are going like this. We want to show that we know this thing moves left to right. With parametrics, they're usually putting something in motion. That's really the whole point of them. So we need to see the way this object is moving. And that's the way it's moving. It's following this path in that direction. That's important. Now, how you can check the direction if you don't want to, if you're not using the calculator. All you got to do is just pick a few points, and let's just see what happens. 2 is usually enough, but 3 is even safer. And let's just see what x is as we do this. That's really all we've got to do. And I can go back to the parametric part. I don't really need to use the function. So originally x was 1/2 t. So if t was 0, 1/2 times 0 is 0. If t is 1, 1/2 of 1/2 times 1 is 1/2. 1/2 times 2 is 1. So as time moves forward, your x-coordinates are moving to the right. And that's really, I mean, you can also find y-coordinates to go with these if you really need to. That's usually enough. So as time moves on, I'm moving to the right. And that's usually good enough to get that direction of motion there. So that's the simplest way to do it. Final example today is taking these two parametric equations, turn them into a rectangular function. It just says to write it as a function, but also want to make sure we graph it. There's a lot going on here. We've got to do the work. We've also got to check the domain. There's going to be a domain issue because of the square root, and it's a rational equation. So there's going to be a few things. Direction's going to be kind of tricky on this. And I'll also show you how to check everything in Desmos in the end, but you got to make sure you can do it without using Desmos so that you've got all the pieces here figured out. So let's do the eliminating the parameter idea first. Let's take this equation. Let's see if we can go ahead and solve for t so we can plug that in down here and finish it up. All right, so first thing I'm going to do, I'm going to multiply both the top or both sides by this denominator, square root of t plus 1. So x times square root of t plus 1 is just 1, because that would go away on this side. Next, I'm going to square both sides. So x squared times t plus 1 is 1. And I'll do it that way so it shows that these are distributed. So next, I'm trying to get t by itself. I'm going to divide by x squared. So now this is gone. T plus 1 is all that's left over here. 1 over x squared on this side. And then finally, let's subtract 1. So 1 over x squared minus 1. That's t. Now we've got t. I'm going to go ahead and plug it in the y equation. So 1 over x squared minus 1. And all that's over the same thing plus 1. So 1 over x squared minus 1 plus 1. Right, well, that part goes away. That's kind of nice. This part, 1 can be turned into x squared over x squared because we need to get a common denominator and combine some things there. So 1 minus x squared over x squared. All that's over 1 over x squared. Because the negative 1 plus 1 goes away. And the way I want to solve this is, or simplify it anyway, dividing by this, so multiply by the reciprocal. So x squared over 1. And the x squareds are going to go away. All that's left is 1 minus x squared. So, sort of the final answer. Let me make that a little simpler. So y equals 1 minus x squared. But that's not fully the picture. We've got a lot of things going on. We've got some domain restrictions we've got to figure out. We've got to figure out the directions things moving. So let's start with trying to figure out the domain restrictions up here. Start at the beginning, back with the parametrics. Well, let's start here. T plus 1's in the denominator, so it cannot equal 0. If it does, we've got a problem. So t can't be negative 1. That's kind of important to know. All right, here, I saved this one because it's a little more complicated. The square root of t plus 1 is in the denominator. So we can't, this whole thing can't be 0. And whatever's under here has to be positive. Now, square root alone, you can take the square root of 0, but we can't have 0 in the denominator. So t plus 1 has to be bigger than 0. Okay? It's got to be positive so I can take the square root of it. And square root alone, it could be 0, but I can't have 0 for my denominator, so we'll go ahead and do that part. So t is going to be bigger than negative 1. Which fits, these two line up perfectly because it can't equal negative 1, and it must be bigger than negative 1. So that's great. I like seeing that. We've got a domain restriction for t, but let's try to translate that into our function for x. So t must be greater than negative 1. All right, so that means that t can be from negative 1 to infinity. So let's look at both ends. Let's see what happens as x approaches negative 1. Or, sorry. Let's see what happens when t approaches negative 1. Let's see what happens when t approaches infinity. So one more time, this is my domain. In terms of time, time has to be bigger than negative 1. So I want to see what happens when it gets really close to -1, because that's on this end. And I want to see what happens as it goes off toward infinity. That should tell me what x is doing. So as t is doing that, let's see what x is doing. Now normally you did is x does something, what's y do? It just makes more sense since our domain is going to end up being in terms of x. And we can start with t here. Let's just, as t does something, let's see what x does. All right, so let's play it out. Let's see what happens if we go back to the x equation, right here. And if I put in -1 for t, all right, so -1 plus 1 is 0. And 1 divided by 0, I know I can't do it, but if I could, it'd be infinity. So that's what x is going to be doing. It's going to be approaching infinity as t is getting close to -1. All right? Now, as t is getting close to infinity, so if I put infinity in here for t, add 1 to it, it's still infinity. Take the square root of it, it's still infinity. 1 divided by infinity is 0. So as you're getting bigger and bigger values of t, your x is getting really close to 0. And you can do the table idea where you pick t coordinates and pick x coordinates, but this kind of takes care of that. So this is enough to give me the direction the object's moving in. So I'll talk about that once I get the graph made. All right, so our domain for this thing, just put a little comma here for domain, where x is greater than 0. So there's my function. And I know that because x is going to approach 0 on one end and infinity on the other. So from 0 to infinity. So x is greater than 0, we cover all that. All right, so that's what it's going to look like. It's 1 minus x squared, where x is bigger than 0. Let's get that on the graph. 1 minus x squared. So intercept at 1. And you can just plug in numbers if you want. You can use the opening pattern. Again, it's up to you. It's going to go over 1 down 1, over 1 down 3, over 1 down 5, but that's getting off the charts, so I'm just going to not worry about it. I'm not putting any arrows on here yet because the arrows need to indicate which direction things are moving. But I'm pretty confident that it's going to be bigger than 0. But honestly, I need to be careful there because it was greater than 0, so I really need to change that and put an open circle. Let's do that. It looks like it's never quite going to make it to 0. That's what the domain's showing me. Now let's see if we can make sense of what's going on as far as the direction this thing's moving. So as time is approaching -1, so that's the far beginning of time in this thing, we're out at infinity. And as time moves forward toward infinity, our x value is getting closer to 0. This thing's moving right to left. It's moving from infinity back towards 0. So this thing's coming from the right, moving left. Again, you can pick some values for t and then see what the x and y coordinates are that match up with those. That works fine. But this is a better way to do it. I think it's a little more efficient. So it's starting off toward infinity and it's moving back towards 0. And it never quite gets there. So just put some arrows on here indicating that it is heading back towards 0. It's heading to the left. And it never quite makes it there. So now we'll jump to Desmos and just confirm all of that. So there's the parabola. Now, I didn't do a domain restriction. I could have. Really, I just need to see this piece of the parabola. So the graph's, it's never going to even get over here. And I've done the table again. X is my x equation, y is my y equation. So there's the parabola that I got for the function. There's the table for the parametrics. And I'm going to put t in motion. Now, I didn't go very far. I went from -1 to 10. You can go as far as you want. We should be seeing this thing move from right to left as time goes forward, and it should never quite make it to 0. So let's see if that happens. Took a while to catch up there. So yeah, it's getting really close. So shoots up really fast and just slowly closes in on 0, but never quite makes it.